All right, it is 10, so let us get started for today. Some reminders, hopefully that I don't remind you of this, but test 4, that would be on Wednesday, I believe, is when we have our test. I think hopefully I'm not, now that I say that, I'm just going to double check that I am not messing you up with my other class. It's one of those days on a Monday where I say something that I'm like, wait, what? Is that actually correct? That's what's on the schedule. Good. So I'm not going crazy. Yep. So you are having your test on Wednesday. As a reminder, the stuff we're going to talk about is not on test 4. So on Friday, I said that our cutoff was resonance structures. So that was our cutoffs for what's going to be on test 4. So even though this isn't on is on the test 4 or in the test 4 folder rather, you won't be seeing this these questions until the final exam, which is going to be cumulative. So just be aware of that. And test 4, you know, this is the 4th test you've taken in this class, so hopefully you know the whole show, how it's going to go down and all that. So octet rules on the final. The octet rule is what we have been doing with our Lewis structures and bonding. That is going to be like that part of the octet rule is going to be on test 4. The stuff where we look at actually making 3D structures, that's going to be on the final. Yeah, so Lewis structures, all that stuff on test 4. Basically anything before this bond length slide is on test 4. That's in the test 4 folder. This is the only, these series of slides that we're going to talk about today, even though they're on the PowerPoint that I had for Friday, it's not going to be on test 4 because we're just talking about them today. All right. So any questions before I go into our material for today? All right. If not, let's talk about covalent bonds and strengths of covalent bonds. And this is a fairly easy topic, I think, because we've already talked about covalent bonds. And we've already talked about what it means to be a covalent bond. So if you remember, a covalent bond is when two non-metal atoms are sharing electrons between each other. And a single bond is when you are sharing 2 electrons. A double bond is when you're sharing 4 electrons. A triple bond is when you're sharing 6 electrons. All right. And the idea is the more electrons you're sharing between each other, the stronger the bond. So if we are comparing atoms and we're saying, you know, what kind of bonds are strongest, first, we can really only make that comparison when you're looking at bonds between like atoms. So what I mean by that is we have 2 comparisons going on. One is the bond strengths when it's only between carbon and carbon. And our second comparison is between carbon and nitrogen. These energies are the strength of the bond. The higher the number, the stronger the energy. So if you just look at the triple bond, you'll see that carbon-nitrogen triple bond is stronger than carbon-carbon triple bond. And you don't know that unless you do an experiment. So I'm not worried about people knowing like that trend. What I want people to understand is that a triple bond is stronger than a double bond, which is stronger than a single bond. All right. So a single bond is your weakest type of covalent bond. A triple bond is the strongest type of covalent bond because you're sharing more electrons. And bond strength and bond length are inversely proportional. That is, the stronger the bond, the shorter the bond length. They are kind of being just pulled into each other when you have stronger bonds. They're being held together tighter so they come closer together. Again, we can only determine bond length when we're looking at like types of atoms. So if I compare different atoms, right, one of these has to be Br if I want to make a trend. And our trend is that this is one column in the periodic table. As I go down the table, bonds become weaker. So here in my comparison, bromine's always my like atom for my comparison, right? Fluorine is at the top of the halogens, then chlorine and bromine. So your strongest bond would be the bromine-fluorine bond. Your weakest bond is the bromine-bromine bond. So just remember, as you go down the column, bonds get weaker. And this is true if you're comparing bonds. Like one atom has to remain static, one atom can't change, and the other atoms can change. Then we can start saying something about bond strength. And as you go across the period, they'll get stronger. So stronger as you go left to right, weaker as you go down the column. So that's our trend for bond strengths. One, the type of bond determines the strength. Two, what atoms are part of the bond also determine the strength. So here's a little exercise that's comparing our Lewis structures and the bond strength idea we just talked about. So I have three compounds here. The first thing you need to do is determine what type of bond is forming between our carbon atoms here. And once you do that, I want you to order compounds by increasing carbon-carbon length and also decreasing carbon-carbon length. So you should first order these from weakest bond to strongest bond, and then longest bond to shortest bond. But you can only do that after you determine what type of bond is between these carbons. So I'll give people like just a few minutes to do this. If you have questions, as always, feel free to send me something in the chat. Otherwise, try and figure this out. All right, so hopefully you had a few minutes to figure that out. What I'm going to do is, since we have a test on Wednesday, let's do the Lewis structures again. So on Friday, I was talking about how chemists, when they write structures, a lot of the time they do it in such a way to tell you how it's bonded. So I did that for you. Just be aware when looking at molecules, chemists don't write carbon hydrogen compounds like this. Really, I should have written this as C2H2, C2H4, and C2H6, but I was trying to make it easy for you so you can actually see how these things line up. So here's our Lewis structure for A. So there's all the valence electrons. So hydrogen always wants 2. So right now it has 2. 2 hydrogens are good. Carbon has 5, 5. So I need to make a bond here. 6, 6. Make a bond here. 7, 7. Make a bond here. 8, 8. So carbon's good because it wants a full 8. So our first molecule has a triple bond. And then our second molecule would have a double bond because you have 2 hydrogens now. And our third molecule would have a single bond because it has 3 hydrogens. Hopefully you're all comfortable with that idea. If not, please let me know. Please contact me. We can do a tutoring session before Wednesday to do more Lewis structures, just so, you know, when it comes to test time, you're not wondering how to do it. All right. So now that I know what type of carbon bonds I have to order them from weakest to strongest. And I'm just going to number these 1, 2, 3, so I don't have to keep writing everything. So your weakest bond is molecule 3 because it's just a single bond, followed by 2, followed by 1. So that's weakest to strongest. Your triple is your strongest. Your single is your weakest. And the longest to shortest actually has the same order. Your longest bond is the single bond. Your shortest bond is the triple bond. The more electrons you have in your bond, the shorter they become. All right, so any questions about bond lengths, bond strengths, or anything that you might have? All right. Weakest to strongest equals longest to shortest. The weaker a bond is, the longer it is. The stronger a bond is, the shorter it is. And if you want to get if you want to know the physical reasons for this, which I'm not really asking you to know, but in case you're interested why that works out, remember that at the center of an atom are your protons, so that's positive charge, right? And a covalent bond is between electrons. And so the more electrons you put between a bond, one, you don't want to break this because you have good magnetism going on, minuses and positives all interacting. And as you put more negative charge between these two positive charges, the positive charges are just going to naturally come closer to this big area of negative charge. So that's why it gets stronger and shorter, because you're just putting more negative charge between two positive entities. Positive entities come closer to interact with the negative charge, and they don't want to be ripped away from there because there's a lot of negative charge there. That's what's happening physically. But again, you don't really need to know that. At Gen Chem 1 level, it's fine to just know the trends. Yeah, I mean, the vast majority of chemistry, to understand it, is understanding how magnets work. because that's all chemistry is, positive, negative charge. You can boil a lot of chemistry down to think of it just like magnets. Like in the Aufbau principle, why don't electrons want to pair up with each other? Why do they want to be alone? Because they're negative charge. Why would you want to be next to another negative charge? So on and so forth. Yep. Chemistry is just mini magnets. All right. So we talked about this idea of bond strength. Now let's actually go into calculations of bond strength. And these are called bond energies. And a bond energy is how much energy it takes to actually break a covalent bond. How much energy do you need to put in to rip those positive charges away from the electrons? You might also see this as bond enthalpy as well. And it's bond enthalpy, so we give it the symbol of delta H. And when we calculate bond energies, we really think of it in terms of how much energy do we get from breaking a bond and how much energy do we get when forming a bond. That's how we can calculate the enthalpy of a reaction. So let me restate that because I probably said that a little jumbled. In a reaction, an important thing to know is how much heat is taken in or how much heat is given out. And we already talked about that concept like a month ago, right? When we were talking about, ice packs, when you have a reaction, it gets colder because it's taking heat in. We can actually calculate that in terms of covalent bonds. That's called delta H reaction. So in a chemical reaction, how much energy do we release when we make new bonds? How much energy do we have to put in to break bonds? And one thing I want to note, and those of you who are going further in chemistry, this is one of the topics that I want you to implant into your brain, because even when we get the biochemistry and students there are seniors at that point, people still get this concept confused. When you are breaking a bond, you need to put in energy, right? You have to put in energy to break that bond. When you are making a new bond, you get energy out. So breaking a bond, a chemical reaction, you are putting in energy, so it would feel cold to you. When you're making new bonds, you are releasing energy into the world, so this will feel hot to you. If you could, if you had a flask and you're holding this in your hand. People always get this confused. So just be aware, if you break a bond, that's positive energy. You're putting energy into the system. If you make a new bond, that's negative energy. Energy is leaving the system. So just something to tuck away in the back of your head if you're going to organic, or if you ever see me again in biochemistry. Yeah, that's just a concept people often get confused about. But let's see how we can calculate the enthalpy change in a reaction. That is, how much heat is given out or how much heat is put into the reaction, based solely on what bonds are being broken and what bonds are being formed. And we're going to do this together, as in I'm going to do it and you can follow along. And then I have a question where you can try this out on your own. So the equation we need is given up here. The change in enthalpy of a reaction, remember enthalpy is a fancy word to say heat. So the change of heat energy in a reaction is equal to giant sigma. Remember, this means sum. So add all these together. So that's the delta H of bonds being broken. Where can we find this stuff? Well, here is a table that tells you how much energy a bond is worth, right? So what this table says is that if I want to break a single carbon hydrogen bond, I have to put in 413 kilojoules of energy. All right, that's what this table says. And so we're going to learn how to use it in a second. So we sum delta H of bonds being broken plus sigma delta H bonds being formed. So this equation, which comes from your book, I'm going to try and simplify, make it more simple for you. And I'm going to show you a different way to use this equation, one that I think is easier. So let's remember in a chemical reaction, the left side of the arrow are our reactants. And the right side of our arrow are products. The way I calculate this reaction is I do delta H reaction equals the sum of delta H bonds reactants minus sum of delta H bonds products. And it might not look it, but these two equations are the same thing. It's just, I think the bottom equation might be easier for students to figure out. So what I want to do to calculate delta H reaction is I just want to count how many bonds I have of my reactants. So on my reactant side, now I'm going to draw out these figures with the Lewis structures. So my first Lewis structure looks like this. Then my second Lewis structure is hydrogen, which look like that. So that's my molecules on the reactant side. Let's do that for the products. So I drill my Lewis structures. Now I just want to count how many types of bonds I have for my reactants. So I have 4 carbon single hydrogen bonds. That's what I mean by counting bonds, just seeing like what type of bonds do I have. So I have 4 carbon single bond hydrogen bonds. I have 1 carbon-carbon double bond, and I have 1 hydrogen-hydrogen single bond. So those are the bonds in my reactants. And on the product side, I have 1, 2, 3, 4, 5, 6. I have 6 carbon-hydrogen bonds. And I have 1 carbon-carbon bond. So that's the first thing we need to do. Just count up the number of bonds. That's step 1. Step 2 is using the delta H equation. So that is the sum of. So I'm going to sum all these together. So I guess I don't actually need that sum off. It is 4 times the energy of a carbon-hydrogen bond, which is 413 kilojoules per mole. So I'm doing 4 times 413 plus, because these are reactants, so I'm adding them all together, plus 1 hydrogen-hydrogen bond. A hydrogen-hydrogen single bond has an energy of 436 plus the energy of a carbon-carbon double bond, which has the energy of 614. So I'm going to add all these together and subtract it from my reactants, which I have 6 carbon-hydrogen bonds. So this has the energy of 413 plus 1 carbon-carbon bond, which has the energy of 348. And then you just do the math to figure out delta H reaction. So let me do this real quick on Excel. And if you have questions, now is a good time to ask them, as I'm just going to do a calculation here really quick. Does that say 413? Yes, that says 413. Three plus 436 plus 614. So the left side of my equation, that is 2,702 kilojoules per mole minus, now I have to do the right side of my equation, 6 times 413 plus 348, which is 2826 kilojoules per mole. And those energy for bonds will always be the same number for certain bonds, like CH will always be 413. Yeah, those are pretty static. They could change based on local environment. By that, I mean in complex molecules, and I'm thinking of proteins because I'm a biochemist. Proteins can create a chemical environment where you surround certain bonds by different molecules, and you can either, and mostly that's done to weaken a bond, so you'll bring that energy down. But that's more of an advanced concept where based on your chemical environment, you change bond strengths. So they're pretty static. They're pretty much fixed. They can change, but we don't have to worry about that. What is on the left side of the equals? That's a 2 with a half parenthesis saying step 2. All right, so we got the energies. Now we just subtract them. 2702 minus 2862. And the energy of this reaction, the delta H, is negative 124 kilojoules per mole. So when we take ethene, which is what this molecule is called, plus hydrogen gas and make ethane, we release 124 kilojoules of energy for every mole of product we make. So that's how we figure out the delta H of a reaction. I would have to give you the chart, yes. I would have to give you numbers. Otherwise, you won't be able to do this problem if I don't give you numbers. So, yep. So on the final exam, what I would do probably for this question is I would give you like a bunch of numbers. And being the devious person I am, I would give you a bunch of numbers you don't need and the ones you do, and see if you can figure out if you can pick out what numbers you need and how to use them correctly. All right, but questions about solving delta H reaction using bond energies or bond enthalpies. All right, let's give it a shot. Here's your question. Same idea. So I have ethanol plus 3 moles of oxygen going to 2 moles of carbon dioxide plus 3 moles of water. So I'm burning ethanol, right? So imagine that like I have a bottle of vodka and I put I don't know, a rag in it and lit it on fire. Molotov cocktail. So I'm burning ethanol. How much energy do you get when you burn ethanol? So use bond energies to do that. Remember, our steps here are draw the molecule out, determine the number of bonds for your reactants and your products, then subtract those two numbers based on our bond enthalpies tables here. So this product can be quite in depth. So I'm going to give you like 5 minutes to go and attempt this. If you have questions, anything, feel free to let me know. If you want to show me your work, a fancy thing you can do is take a picture of it and like email it to me, and then like tell me in chat you sent me an email, and I can tell you there. If not, if you don't want to go through that trouble, yeah, just do your best to try and explain it to me. Otherwise, yeah, let's try to get this. If you get stuck, let me know, please. Otherwise, I'll be back in a few to go over this. So if you were to ask this question on the exam, you'll give us a chart? Probably. How would you write out 3O2 as Lewis structure? We can go over O2. So oxygen has 6 valence electrons. The goal is to get to 8. Every time you make a bond, you gain an extra electron. So if I make 2 bonds, that puts it at 8. So that's oxygen, double bond O. And you just have 3 molecules of it. That's what the 3 means. Meaning you have to write out the O double bond 3 times. Yeah, so you have 3 double bond, OO double bonds. That is correct. Oh, I was on mute when I was saying that, wasn't I? So in case you were wondering where to find it on the table, that's O2 down there. All right, so hopefully you made some progress with that. Let's take a look at first our Lewis structures, since that is what we have a test on Wednesday. So make sure we just have the concept of Lewis structures down. Again, making it easy on you to show you how things are bonded. So carbon with 3 hydrogens. Carbon with 2 hydrogens. And that's a single bond to hydrogen. That is just me being fat fingered with my drawing utensil. All right, so single bonds all around for ethanol. And we just went over oxygen. So I have 3 of these. So these are my reactants. Here's my products. I guess I can do prod. So carbon dioxide. Let's actually look at carbon dioxide. So carbon, 1, 2, 3, 4. Oxygen, that's 6. Oxygen has 6. So you're going to need some double bonds. Oh, that worked, I guess. I'm going to draw a nicer. So that's carbon dioxide. Double bond between each carbon and oxygen. So I have 4 carbon oxygen double bonds because each molecule has 2, and I have 2 copies of that molecule. And then H2O looks like that, so it's single bonds. I have 3 of those, so that's 6 oxygen, hydrogen single bonds. So there is our list. So we have 1, 2, 3, 4, 5 carbon, hydrogen single bonds, 1 carbon, carbon single bond, 1 carbon, oxygen single bond, 1 oxygen, hydrogen single bond, 3 oxygen, oxygen double bonds, and there's our product side. So before I move on with putting in the numbers, does anyone have questions on how I got those molecules or anything up to this point before I go on? And if you're typing, what I'm going to do is I'm just going to type, write out what the reaction looks like for delta H. So 5 times CH plus 1 times CC plus, and then I guess I don't need the 1, so plus CO plus OH plus 3 times OO. And that's all going to be minus, in parenthesis, 4 C double bond O plus 6 oxygen hydrogens. And I'm going to put the numbers right above here. So carbon hydrogen is 413. Carbon carbon's 348. Carbon oxygen is 358. Oxygen hydrogen is 463. O2 is 495. Carbon oxygen is 799. Oxygen hydrogen is 463. Why on the chart is it O2 equals 495 rather than showing the double bond of O being 495? I'm guessing the reason they did that is because when 2 oxygens are bonded together, the only molecule that happens in is O2, right? You're never going to get this happening outside of O2. So this happens like once in nature that we know of. And it's a pretty important molecule that it happens to, oxygen. So stylistically, I don't know why they did it. Like, to me, it would make sense to just do that as well, because everything else is in bonds, but that's the reason, I would guess, is that it happens in exactly one molecule, double bonding oxygen. All right. Let me pull out Excel. Whoops. To do this math. 5 times 413 plus 348 plus 358 plus 463 plus 3 times 495. Right, so the left side of our equation, I got, whoops, didn't mean to turn off sharing there. I got 4,719 for your reactants, your left side of the equation. Let me just double check. 5 1 times 3 plus 348 plus 358 plus 463. Yep, that looks good. The left side of the equation, 463. The left side of the equation is 5974. So when I subtract those two numbers together, it is negative 1255 kilojoules per mole. So when you burn ethanol, it releases energy, which makes sense because burning ethanol is hot. You create a fire. Can I read out what the formula says? The formula is 5 times 413 plus 1 times 348 plus 358 plus 463 plus 3 times 495 minus 4 times 799 plus 6 times 463. And the words say CH. I'm going from left to right. CH, CC, CO, OH, OO, CO, OH. Maybe it'll be better if I put the parentheses in a different color. So everything in this red brown are parentheses. And it's just the bonds I have listed above. I was just putting them in order. Let's see here. Maybe this would help too. CO plus OH. Let me do parentheses for that. Yeah, I'll just type it out. Probably easier than reading it out. That's all one thing. Let me stretch this out. That's the left side of the equation. Minus OH. That's what the equation says. Right. Any other questions before we call it a wrap? This may sound weird, but I think this is kind of fun. I mean, the only reason I got into chemistry was because, so I hated school as a kid. Like I skipped so much school as a high schooler. It wasn't even funny. Like 30 days a year at least. But the one class I did enjoy was chemistry. One, I liked doing the experiments. Two, I liked doing the math. The math made sense to me, right? It has a logic to it because all these calculations are made by humans, right? To try and explain what's going on in the world, right? Because humans are a very logical species. We love to put numbers to things. So doing this made a lot of sense to me. So I also agree that it is fun. Most of your classmates, based on what I see in my reviews, disagree with that, but I'm glad some people do. So I'm glad some people find this fun. All right. If there are no questions, please let me know if you do have questions about anything up the test score. I'm available pretty much all Monday and Tuesday, except after 3 Monday, or I guess today, pretty much all Tuesday except 12:30 to 1:45. I appreciate that. But yeah, let's see. Friday, we will go over the lecture we had for Monday. That will be on the final. So that'll be on the final exam. Next week are reading days before the final. What I might do is I might put up like a timesheet where like we can get together and have like a final exam together. Let's study for it. But I have to know what time people will be available for that. So I might do like something where you can go online and put in what time you'd want me to do that, and whatever the majority is, we can do that. Otherwise, that's just, you don't need to worry about that yet. I'm just getting stuff that I've been thinking about off my head. Otherwise, good luck on Wednesday. Hopefully I'll see you on Friday, and have a good rest of your week. Take care, everybody.